Hi everyone, welcome back to my channel Chiro's Aspirations. It was a long time after the first video. I was very busy in digital marketing and lots of many trainings. I was addressing many gatherings. Anyway, I'll compensate it. And the people who are new to my channel, hi, this is Chiranjeevi, maths trainer and a motivational speaker. And the people who are new for this channel, please go to the description and click the link and go to my previous video, learn the basics and come back to this video. We'll learn many things. So shall we go? Yeah, it's an amazing concept. Lots and lots of mathematical concepts sometimes people feel difficult. So it was long back ago. So Fibonacci discovered the Hindu Arabic numbers. And later on, at that time, it was very difficult for dividing a number. So Euclid came with a method of division. So dividing a number. We'll be learning this Euclid's Division lemma and all those things in today's video. Shall we go? Yes, we'll go with it. And I have a great surprise for you. Watch the video till the end and the surprise is for you. 50 divided by 10. So this becomes dividend and this becomes divisor. So if we divide 50 by 10, we'll be getting 10 5s are 50 and the remainder is 0. So this becomes quotient and this becomes remainder. And this is divisor and this one is dividend. This is the actual division we have, right? 50 by 10. So the 10 divides 50 exactly. Hence we have the remainder 0. The same division we can write like this: dividend is equal to divisor into quotient plus remainder. Can you write like this? See, this is the dividend 50, that will be equal to divisor is 10 into quotient is 5 plus remainder is 0. So LHS is equal to RHS. So this holds good for the general division. Same for even the Euclid's division lemma also states the same thing. So whenever some integer a is divided by b, for example, b divides a, such that an integer c arises and remainder. So here, instead of c, I will be taking q. So a is equal to bq plus r is the division lemma. And here the r will be in between 0 and b. The remainder always will be lesser than b. Obviously, b is nothing but a divisor, right? So this is the Euclid's division lemma. Generally, lemma is nothing but proven statement. So it's nothing but proven statement. So this proven statement, so here we have a is equal to bq plus r, where a is some integer and b is also some integer, q is quotient and r is remainder. Always this r will be in between 0 and b, that is divisor. For example, we have taken here 50 by 10. See, 50 is equal to 10 into q is 5 plus r is 0. See, this r should be equal to 0 or greater than 0 but less than b, less than 10. See here, 0 is less than equal to 0 or less than 10. Okay, obviously it is equal to 0, right? So it happens like this. Now if we consider any number, for example, we'll take 10 by 3. So if we divide 10 by 3, it becomes 3 3s are 9 and the remainder is 1. So what happened? According to the Euclid's division algorithm or the Euclid's division lemma, so it is 10 is equal to 3 into 3 plus 1, where 10 is some integer, 3 is some integer and this 3 is quotient and 1 is the remainder. So here again I state, so this condition R is between 0 and B. Here B is nothing but 3. So what happens? For this condition we have the remainder lesser than 3. So 0 to 3. So therefore the remainder becomes 0, 1, 2. So this is the possibility of the remainder when we divide any number by 3. I hope you people are understanding. Now we'll go with a simple thing, that is, as we know, so A is equal to BQ plus R is the Euclids Division lemma, where R will be between 0 and B. So B is the divisor, A is the dividend, Q is the quotient and R is the remainder. We know this. Okay. So this particular Euclid's lemma we use in various aspects of mathematics. Like if we divide some number by 3, let's take for example some integer, let some integer be A. Now I'm going to divide this A by 3. I'm going to divide this integer A by 3. What's going to happen if I take the actual division method? So A 3, this is quotient and some integer will be getting here, and here it is remainder, right? Can you take like this? A is equal to 3 into Q plus R. According to the rule, always the R is lesser than or equal to 0 and it's between B. Here the B is 3, right? So it is 3. So R is between 0 and 3. Therefore, the remainder possibility is 0, 1 and 2. So this can take these 3 things, not more than this. Whatever the number we divide, for example, 18 by 4. So it's 4 4s are 16, again 2 remainder. Remainder will be always lesser than the divisor. Whatever the division you can take, 100 by 50. 52s are 100, again 0. This remainder is always lesser than this divisor. Here it is 50. Whatever the division you can take, so it is 48 divided by 2. So 2 4s are 8, again 0. This is less than 2. So the possibility when B is 2 is it is 0, 1. That's it. So the overall concept is whatever the number you are going to divide by any number. For example, you take A by 4. So here we have 4, which means A is equal to 4Q plus R. The remainder is between 0 and B. So the possibility of the remainder is 0, 1, 2, 3. When we divide by 5, it is R is equal to 0, 1, 2, 3, 4. When we divide by 6, R is equal to 0, 1, 2, 3, 4, 5. Are you following? So always it will be, the remainder will be less than the divisor. So this is Euclid's division lemma. Whatever the number we take, we divide that particular number by a number, an integer by any number, so the remainder will be lesser than that number which is dividing the number. Here if we take for example 10 by 3, so 10 divided by 3 is 3 3s are 9 and again 1 is the remainder. So 10, this number 3 is dividing, so 3 times we can find 3, right? So 3 times we can find 3 and 1. So this gets multiplied and 1 is remaining. So always the remainder will be lesser than the number which is dividing. I hope you are following. Now for solving this problem, we have, let's go for the solution. So let me consider integer. Let an integer be a. Let an integer be a. I am going to consider an integer a. Now, according to the Euclids, we have from Euclids Division lemma, a is equal to bq plus r, where r is between 0 and b. So here we have b is equal to 6. Whatever the form they are given, to prove, we need to prove that any positive even integer is in this form. So here if you take 6q plus 2 and 6q plus 4, you can observe here 6 is nothing but b. So we are going to consider b as 6. Now substituting this b in the Euclid's division lemma, it becomes a is equal to 6q plus r, where again r is between 0 and b. Here b is 6. So now the remainder is between 0 and 6. Also we have equal sign also. So the remainder becomes 0, 1, 2, 3, 4, 5. So it is less than 6. Here there is no equal sign. So it should be below 6. So I am going to consider up to 5. So these are the possibilities of the remainders when we divide a number by 6. Now here I am dividing a by 6. So I will be getting all these things. So first let me consider if r is equal to 0. What happens to this a? Let me take this as equation 1. So a is equal to 6q. Isn't it? Here r becomes 0. So if r is equal to 0, a is equal to 6q, and this becomes 0. This can be written in the form of 2 into 3q. So that is equal to 2m, where m is equal to 3q. Can we write like this? Here what I am doing, I am substituting. First case I am taking when r is equal to 0. When r becomes 0, a is equal to 6q plus 0, that is nothing but 6q. So this I am going to split as 2 into 3q, that is equal to 2m. Here this m is nothing but 3q. Why I am doing this is, I need to show this number is in the form of even. The multiples of 2 are nothing but even numbers, right? So 2 into any number obviously will be an even number. So that's the reason I split this into 2 into 3q. So that is equal to 2m, where m is nothing but 3q. Understanding? Yes. Next condition we are going to go when r is equal to 1. So first condition r is equal to 0. Next r is equal to 1. Again same thing I will be substituting here. So a is equal to 6q plus 1. So here I cannot split it because I cannot take any common here. So I will keep this as it is, 6q plus 1. Next I am going to the second condition, that is r is equal to 2. So a is equal to 6q plus 2. So now I can take common, right? So in the place of r I have substituted 2. So I can take 2 common. So that becomes 2 into 3q plus 1, that is equal to 2m, where m is equal to 3q plus 1. Understanding? Here a is equal to 6q plus 2, that is equal to 2 I have taken common, so 3q plus 1. The entire 3q plus 1 I am making it m. So 2 into any number obviously is an even number. Here so far how many even numbers we got? We got one even here and another even here, and this becomes obviously odd. Let us take the remaining thing. Okay, right, no? Okay. If r is equal to 3 I am taking, so it becomes, again I am going to substitute here, a is equal to 6q plus 3. I cannot take 2 common, I can take 3 common, but it becomes multiples of 3. So I will keep this as it is. So when r is equal to 4, a is equal to 6q plus 4. Again I can take 2 common, so this is 3q plus 2, that is equal to 2m, where m is equal to 3q plus 2. Are you able to follow? Yes. Again I am going to take r is equal to 5. So a is equal to 6q plus 5, that is equal to, I cannot take anything common. I'll stop. See, since we are dividing the number by 6, any integer, we have considered an integer a and dividing that by 6. So we have a is equal to 6q plus r, where b takes the value of 6 and the remainder is always between 0 and 6, which means the b. So here, so that was the possibility, that is r is equal to 0, 1, 2, 3, 4, 5. And now what happens? So one by one we are going to consider. That is, first I considered r is equal to 0. I substituted r in equation 1, that is this equation, a is equal to 6q plus 0. That becomes 6q. I can take 2 common because here the question is about even and odd. So multiples of 2 are nothing but the even numbers, and we have taken 2 common, and 2 into 3q is again 6q. So this 3q I made as m, so 2m. The multiples of 2 are obviously even. So I got this as even. Next condition, in the next case, I have substituted r is equal to 1, a is equal to 6q plus 1. In the next, r is equal to 2, a is equal to 6q plus 2. Again I have taken 2 common here and it becomes 2m, again it is a even. Here also r is equal to 3, so a is equal to 6q plus 3. Here we cannot take 2 as common. Here r is equal to 4 and a is equal to 6q plus 4, that is 2 into 3q plus 2. And again r is equal to 5, a is equal to 6q plus 5. If you observe, 3 even numbers we can see, that is if r is equal to 0, if r is equal to 2 and if r is equal to 4. So it is in the form of 2m, right? 2m, 2m and 2m. So here the question is, show that any positive even integer can be in the form of 6q, 6q plus 2 or 6q plus 4. If you observe 6q, see here 6q, it is in the form of even number, right? 6q plus 2, 6q plus 2, it is in the form of even number. 6q plus 4, it is in the form of even number. So by looking at this, we can confirm that therefore the positive integer or any positive integer is in the form of even integer that is 6q, 6q plus 2 and 6q plus 4. Okay, we have proved that any positive integer, even integer, will be in the form of 6q plus 6q, 6q plus 2 and 6q plus 4. This is the answer. This way we can take different things and solve. The same question they can ask for only positive integer. So all the things are positive integer, right? You can take from starting from 6q, 6q plus 1, 6q plus 2, 6q plus 3, 6q plus 5 and 6q plus 4. Everything is positive integer. If for example they ask a question like, show that any positive integer can be in the form of 6q, 6q plus 2 or 6q plus 4 or 6q plus 3, all these things you can solve it. You can show that all these are positive numbers. Or they can ask another type of question that, show that any positive odd integer can be in the form of 6q. Here if it is odd, 6q, 6q plus 2, 6q plus 4 will not be there. Then you need to do the same steps, but you need to change the sentence that, so here 6q, see 6q, this is even, so this is not odd. 6q plus 1 is odd, 6q plus 3 is odd, 6q plus 5 is odd. So the question changes. It tells that, show that any positive odd integer can be in the form of 6q plus 1, 6q plus 3 and 6q plus 5. So this way, whatever the question they change, you can answer. The procedure is same, taking the Euclid's division lemma, but the solution, the end step, what you are going to write the sentence, you should be careful while proving it. Now we have another type of problem here, that is, show that exactly one of the number n plus 2 or n plus 4 is divisible by 3. So here they are stating that exactly one of the number is divisible. So we need to check many cases. Let's go for the solution. Here they are given is divisible by 3, which means they are giving b as 3. So as usual we know in the solution side by let me take like this. Let the integer be n. So according to the Euclid's division lemma, we have n is equal to bq plus r. Instead of a, I have considered as n. So n is equal to bq plus r, where r is between 0 and b. Here divisible by 3, which means they are speaking about b. b is 3. So n is equal to 3q plus r, where 0 less than equal to r less than 3. So here from this we can see that r is equal to 0, 1, 2. This is the condition arises. So therefore, if we substitute this 0, 1, 2 here in n, we will be getting n is equal to 3q when r is 0, 3q plus 1 when r is 1, and 3q plus 2 when r is 2. So these three cases will be getting. Now the question is, they are asking that we should show that exactly one of the number n or n plus 2 or n plus 4 will be divisible by 3 if we take three conditions. So first let me consider case 1 when n is equal to 3q. See, if n is equal to 3q, so then actually it is divisible by 3, right? This is divisible by 3. So that n is divisible by 3, we can write like this. See, for example, if you take some number like, okay, so n is divisible by 3 because we have a remainder here 0, right? So when the remainder is 0, then we will be telling that it is exactly divisible. Okay, so again the same thing I am going to take for n plus 2. First we took n plus 2 and n plus 4. For n plus 2 I am taking like that. So n plus 2, that is equal to, in the place of n I am going to substitute 3q plus 2. Is this divisible by 3? No, because this number has a remainder 2. So n plus 2 is not divisible by 3. So n plus 2 is not divisible by 3. Okay, the same thing we are going to consider n plus 4. n plus 4 is equal to, in the place of n I am going to substitute again 3q because this is the case we have taken. So 3q plus 4. Again if you see there is some 4 as a remainder. So again n plus 4 is not divisible by 3. If you observe in the case 1, when we take n as 3q, so n is divisible by 3 when we consider the n, the first n. If we take n plus 2, in the place of n I am going to substitute 3q, it becomes 3q plus 2. So again n plus 2 is not divisible by 3, this n plus 2, because we have a remainder as 2. So again if we consider n plus 4, in the place of n again I am substituting 3q, that is 3q plus 4. So here also there is some remainder, so it does not exactly divide. So n plus 4 is not divisible by 3. This is case 1. If you consider case 2, here the first case is 3q. Now I am going to consider n as 3q plus 1. So n is equal to 3q plus 1. Again taking this, n is equal to 3q plus 1, the first n I am going to consider here for the case 2. So directly I can tell that there is some remainder here. So n is not divisible. by 3. Again, if I consider n plus 2, n plus 2 is equal to the place of n. Again, I am substituting 3q plus 1 plus 2, that becomes 3q plus 3. Again, there is some remainder here. So, n, okay, you can take like this. If you observe here, that is equal to 3 into q plus 1. Can you take like this? Again, this is in the form of 3m, where m is equal to q plus 1. Okay, so it is in the form of 3m, which is multiples of 3. So anything multiplied by 3 will obviously divide 3, right? So 3 can divide that number. So therefore, this is divisible. So n plus 2 is divisible by 3. The third one I am going to consider n plus 4, that is equal to, in the place of n, again I am putting 3q plus 1, 3q plus 1 plus 4, so that is equal to 3q plus 5. So again I have got some remainder here. So here n plus 4 is not divisible by 3. So this is case 2. What we have done in the case 1, I took n is like 3q. In the case 2, I have taken n is 3q plus 1 and substituting all these values in the 3 cases what they have given. Okay, so here you observed in case 1, n was divisible by 3, n plus 2 and n plus was not divisible by 3. Understanding? The same way in case 2, if you take 3q plus 1, what happened? N was not divisible by 3 and also n plus 4 is not divisible by 3. Only n plus 2 was divisible by 3. What's happening here? They are telling that show that exactly one of the number n plus 2 or n plus 4 is divisible by 3. They are clearly indicating in the question that any one of the number will be divisible. In the case 1, which was divisible? So n was divisible by 3. Other two cases were not divisible by 3. Similarly, if you take case 2, n plus 2 was divisible by 3, n and n plus 4 not divisible by 3. Obviously, in the case 3, if we consider n is equal to, now I am going to take this 3q plus 2. First case finished, second case, and this is the third case I am going to take, that is 3q plus 2. So similarly, if I take the same cases, n is equal to 3q plus 2, again this is not going to divide by 3 because we have a remainder 2 here. So what happens? n is not divisible by 3. Again I am going to take n plus 2. n plus 2, in the place of n I am substituting 3q plus 2. So 3q plus 2 becomes 3q plus 4. So again I got a remainder here 4, which I cannot take anything common here. So n plus 2 is not divisible by 3. The third case I am going to take, that is n plus 4, that is equal to, in the place of n I am going to substitute this one 3q plus 2, that is 3q plus 2 plus 4, that is equal to 3q plus 6. Again I can take common here 3 into q plus 3, where that is equal to 3m. So where m is q plus 3. So again this is in the form of 3m, that is multiple of 3, where this number can be divided by 3. So therefore n plus 4 is divisible by 3. Okay. So did you follow? As per the question, so show that exactly one of the number n plus 2 or n plus 4 is divisible by 3. Since b is 3, by Euclid's division lemma, we have taken n is equal to bq plus r, where n is some integer. So by taking this as the previous problem how we solved, we got r is equal to 0, 1, 2. Now here we 3 cases arises, because when we substitute the 0 here it becomes 3q, 1 here it becomes 3q plus 1, 2 here it becomes 3q plus 2. Now first case I am going to take, that is n is equal to 3q and n is divisible by 3, because the first thing here I am going to take. And the second one is n plus 2. In the place of n I am going to substitute this 3q, so it becomes 3q plus 2. n plus 2 is not divisible by 3, because here there is some remainder. So exactly divisible, the remainder should be 0. So here there is some remainder, so it's not exactly divisible by 3. Even n plus 4, I substituted n is equal to 3q here. Again I got 3q plus 4. N plus 4 is not divisible by 3 because we have some remainder here. Similarly, in the case 2, what happened? We took n is equal to 3q plus 2. Sorry, 3q plus 1. This one. So 3q plus 1. Again I substituted. I got this one as divisible by 3 because 3 into, I can take this 3 common and I got this, and that will divide 3. So these two didn't divide. In case 3, this divided, but these two didn't divide. So as a result, we have proved that. Okay. So in each cases, exactly one of the number is divisible by 3. So such type of problems, there are many other problems. I have chosen some different problems from the previous year question papers. If you have any doubt in any problem, if you need me to solve, you can put that in the comment section, and I'll be coming up with a newer video solving all those problems. Anyway, I hope you have enjoyed these mathematical problems, and as I said initially, there is a surprise for you, and that surprise is every week I will be giving some videos. What is that videos? Mathematics is all about practical applications and practical situations, and I have modules and I have many plans of giving you every week a mathematical application in a real life. I hope it's very interesting, and if you like this video, like it, comment and share, and don't forget to subscribe my channel. We'll have a great journey through mathematics, and we will go. Thank you. Have a nice mathematical time, and bye bye. Take care.